So one very useful application for Laplace domain analysis is that we can apply it to electric circuits. In this video I'm going to go through an RLC circuit. So this is a passive circuit with passive circuit elements, and we're going to find the corresponding transfer function that's associated with the circuit. This is an RLC circuit that contains all of R, L, and C. So we have resistors, we have an inductor, and we have a capacitor. We see here in the circuit diagram, we start with an input voltage over here on the left-hand side. We have a resistor with resistance R1. We have a capacitor with capacitance C. We have an inductor with inductance L. We have another resistor with resistance R2. And we have our output voltage, which is measured across this resistor R2. So for this video, we're going to find the transfer function h of s. And that's going to be the ratio of the output voltage to the input voltage. If we find the h of s for this given circuit, then we can find the output for any given input. So that is very useful in circuit analysis. We'll start with a time domain representation. So we have here for either of these resistors, we know that the voltage that's across the resistor is going to be equal to the current through the resistor times the value of the resistance. For our capacitor, we have that the current through the capacitor is going to be equal to the capacitance C times the time derivative of the voltage across the capacitor. And then the voltage drop across the inductor, I'm going to write that with an L to differentiate that from our input. It's going to be equal to the inductance L times the derivative of the current through the inductor with respect to time. So each of these expressions here can be converted into the Laplace domain, so that will make it a bit easier then for us to apply the necessary circuit analysis. This first expression here, we will just get VR uppercase of s. So our convention is to use lowercase letters in the time domain and uppercase letters in the Laplace domain. That's going to be equal to IR of s times R. Our current here, if we rearrange this first, we will get VC of 1 over C, then times the integral of IC dt. And now if we take the Laplace transform of this expression, we will get here on the left-hand side VC of s. And on the right-hand side, we will end up with IC of s over s times C. And then finally for the inductor, we will get VL of s is going to equal s times L times the current IL of s. For this case, that integration is corresponds to dividing by s in the Laplace domain, and derivative corresponds to multiplying by s. Now we can go ahead to applying our circuit analysis. So we'll apply Kirchhoff's voltage law across each of these loops. So we know that all the voltages around a loop have to be equal to 0 when we sum them up. So we'll start first with the left loop. That'll give us our first equation to work with. And we can see here, if we convert this voltage gain right here, we can just write this as VI of s. So the gain here will be equal to the gain here plus the gain here. We will say that we have two currents in particular. We have an I1 of t that goes through, comes out of the voltage source and goes through the resistor. And we'll define an I2 of t. That one comes through the inductor and through this resistor. So now our voltage gain across this voltage source will be equal to the drop across here and the drop across here. So we will get in the Laplace domain I1 of s times R1. For the voltage drop across the capacitor, we need to write the current through the capacitor divided by SC. Here the current coming through this capacitor is going to be I1 minus I2, because the currents coming in and out of this node have to be equal to 0 if we sum them all together. So we will end up with I1 of s minus I2 of s all divided by s times c. Now we can take care of our right loop. This will give us our second equation. Yeah, once again, the voltage drop across here will be have to equal to the voltage drop across the inductor and resistor R2. So we can write this on the left hand side, we'll write the inductor voltage and then this resistor voltage. So we will get S times L times here the current is I2 of S, and then across the resistor we'll just have R2 times R2 of S, and then we get the voltage drop across the capacitor, which is again I1 of S minus I2 of S over S times C. Now to make the notation a bit simpler for the rest of this question, we're going to drop the of S's. So we'll leave out the brackets and S's. It'll be understood that we're doing everything in the Laplace domain. I'll start now by trying to rearrange this expression for the second loop so that we get a single equation with I1 of S on one side. So if we take this left-hand side, multiply it by SC, and then add I2 of S, that will be equal to I1 of S. So if we write that down here in full, we'll get I1. Again, we're dropping the of S's just to simplify the notation a little bit. We will get S times C multiplied by S L I2 plus R2 I2 and then plus I2. Now we can take this expression for the current I1 and substitute it back into equation 1 where we see I1 here. So on the left hand side we still have our VI. If we take out I1, we're left with R1 plus 1 over SC. So we get R1 plus 1 over SC multiplied by I1, but I1 is equal to all this term here. So we get SC times SL I2 plus R2 I2 plus I2. Then what we're left with here in this original expression is minus I2 over SC. So VI, first we can see that we get 1 over SC plus I2 minus I2 over SC, so those will cancel out. So all we have to worry about then is everything here to this side. So we get R1 times S squared LCI2. So I'll write that as S squared R1 LCI2. We get R1 times SC times R2I2. So we get plus S R1 R2 C I2. We get 1 over SC multiplied by SC multiplied by what's inside here. So we can just go right to writing this inside here. So we get plus S L I2 plus R2 I2. All the terms here contain R2, so we will take that out and simplify this a little bit more. We're left with I2. Now that's outside of S squared R1 LC plus, I'm going to take that common S also now outside the two of these. So we'll get S outside of R1 R2 C plus L. And then the only other remaining term is plus R2. Okay, we're also missing the R1 times I2 term. So we get also here R1 I2, which when we pull out the I2 here, we get R2 plus R1. There we go. Now we're getting close to the end. We have this expression for VI in terms of I2, and then all of our passive elements and powers of S. If we want to write the output voltage VO, we do note that VO in the Laplace domain is just going to be equal to R2 times I2 What this lets us do is jump to our transfer function, h of s, which is equal to VO of s over the input voltage of s. VO is just I2 times R2. VI we found here is I2 times all of this. So the I2 currents will cancel out, and we'll be left with R2 in the numerator. Then in the denominator, we will have s squared R1 LC plus s times R1 R2 C plus L plus R1 plus R2. And that is our S domain transfer function that we can then use for any kind of input to find the corresponding output signal. And we can do this by writing that the output y of s is going to equal our input x of s times h of s. So with the help of the Laplace transform and the inverse Laplace transform, we can take this expression here, combine it with a time domain input signal, and determine what the time domain output signal would need to be. Okay, thanks for watching. Let me know if you like this video. Feel free to comment and subscribe if you're interested in seeing more of this series on signal processing. See you next time.